Give the domain and range of the relation. So for just a little bit of review, let's talk about what domain and range are. All the domain and range are the x and y values. So when we look at these ordered pairs, the domain is made up of all the x values. So that would be the first values of the ordered pair. So in this case, the domain would be 10, -3, 4, and 1. The range is simply the second values because it's our y values. So it'd be 8, -5, 4, and 1. Use the graph to determine the function's domain and range. So what we need to do is see what x values are included in graphing this particular function. So when we look at the graph itself, we know that the graph continues indefinitely down in both directions. So what values, if you look on your x-axis, so only focus in on the x-axis in determining your domain. So when I'm looking on the x-axis here, points that go all the way to -infinity would have been included in graphing this function. Where does the graph stop on the x-axis? It doesn't. It keeps going because there's points as we move to the right that would have been used to graph this function. So our domain would be all real numbers. Our range are our y values. How far down does the graph go? What's the lowest y value? And where does the graph stop as we move up the y-axis? So again, you're going to pay attention to the y-axis. How far down does this graph go? This graph continues down forever. So the smallest y value would be -infinity. Now, as we head up our y-axis, what's the highest point that it hits? The highest point of this graph occurs at y being 4. So we would have 4 as our endpoint. Since 4 is an actual point that's included, we would use brackets. So for our domain, we're going to be looking at our x-axis, and for our range, we're going to be looking at the y-axis. Our next example. Use the graph to determine the function's domain and range. So again, if you're looking at the graph, this graph continues indefinitely to the left and indefinitely to the right. So what x values, if I'm looking down my x-axis, what's the smallest x value? Well, it continues indefinitely to the left. And where does it stop? Well, it continues indefinitely to the right. So again, our domain is all real numbers. So the smallest being -infinity and the largest being +infinity. Now our range, remember, you're going to be looking at the y-axis. So we're going to start at -10 and work our way up until we hit our first point. Our first point, which would be our lowest point, is 0. So our range has the smallest point at 0. So we continue up the y-axis until we get to the top of the graph. The top of the graph is at 4. And that would be included as well. So our range are all the values from 0 to 4, or the lowest point to the highest point on the graph. Let's do one more. So if we're looking at the domain would be all of the x values that were used to graph this function. So keep in mind this graph continues indefinitely up and at a slight angle in both directions. So if we're looking at our x-axis, there would be a point associated with any value to the left, because as we move up this point would be affiliated with that. And same thing as we move to the right. So as this graph goes higher, the x values are getting higher as well. So what x values were used? All x values. So our domain would go from negative infinity to positive infinity. Now when we look at our range, we're looking at our y-axis. So we'll start at -5 and work our way up. So when we start at -5 and work our way up, we hit the first point on the graph at -2. So the lowest point on this graph is -2. What's the highest point? Well, as we keep moving up, the graph keeps getting higher and higher and higher and doesn't stop going up. So it goes to infinity. So the lowest point on our graph is -2, and the highest point is infinity. What's the point furthest left? Negative infinity. The point furthest right? Positive infinity. So let's find the domain of some functions. So in finding the domain, we keep in mind the restrictions. So when we look at a rational function, that is fractions, what is the restriction to a fraction? It has nothing to do with the numerator, but remember that our denominator cannot equal 0. So we know that x minus 9 cannot equal 0, nor can x plus 4. So we solve. So we know that x cannot equal 9, or else it would make our denominator 0 with our denominator x minus 9. And we know that x cannot equal -4, because if -4 were replaced for x, it would make our denominator under the 2x 0. So now we need to state this in interval notation. So again, the easiest way is to come to your number line and put in your boundaries, starting with your smallest point to your largest point. So remember, the only restriction is that it can't be those two values. It can be any other part of the number line. So it could be those values that are to the left of -4. It could be those values in between -4 and 9. And it can be those values greater than 9. So in writing that in interval notation, the first interval is from -infinity to -4, all with parentheses because it doesn't include our endpoints, union with the second part here, which would be from -4 to 9, union with the last part, which begins at 9 and continues to positive infinity. So our domain is all real numbers except for -4 and 9. Our next function, g of x equals x squared plus 3x plus 2. So we look at this function, and there are no restrictions. I can use positive numbers, I can use negative numbers, I can use decimals, fractions, etc. Since there are no restrictions, then we can use any number on the number line, so we can use any value between -infinity and positive infinity. So these quadratic functions will have domains being all real numbers. Our next example, h of x equals the square root of 2x minus 3. Remember that underneath a radical sign, the radicand has to be 0 or positive. So the way we state that is we take the radicand, which in this case is 2x minus 3, and set it greater than or equal to 0. Then we solve. So we'll add 3 to both sides, and then divide by 2. So we know that x has to be greater than or equal to 3/2. So again, come to your number line, put in your boundary point, which in this case is 3/2. Read from your variable. So you read from x. So x is greater than or equal to 3/2. So if it's equal to 3/2, it has a bracket. The values greater than are to the right. So in interval notation, we have 3/2, which is the smallest value. And our largest value, since it continues indefinitely to the right, would be infinity. So our interval would be 3/2, comma, infinity, with brackets in front of the 3/2 and a parenthesis after the infinity. Our next example, we have x over the square root of x minus 10. So we have two restrictions. The first restriction is that the denominator cannot equal 0. The second restriction is that since we have a radical, x minus 10 has to be greater than or equal to 0. So initially, we would think to set up this problem as x minus 10 is greater than or equal to 0 because of the x minus 10 being underneath the radical sign. But the fact that the square root, that radical, is in the denominator, it can't equal 0. So whenever we're setting up this problem, 0 can't be a part of the solution. So we'd set it up as x minus 10 is greater than 0. So we'll add 10 to both sides. So x would have to be greater than 10. So again, let's come to the number line, put in our boundary point, which is 10, read from our variable x is greater than, so greater than is to the right. Since it's not greater than or equal to, 10's not included in the solution. So the smallest point in our interval is 10, the largest is infinity, and in this case, both would be in parentheses. So we're finding the domain of f times g of x when f of x equals the square root of 7x plus 3 and g of x equals the square root of 5x minus 6. When we're multiplying, we can look at the restrictions for each one of these separately to begin with. So since they're both underneath the radical sign, we know that the radicand, 7x plus 3, and 5x minus 6 have to be greater than or equal to 0. So now we'll solve. So we'll start by subtracting 3. So we have 7x is greater than or equal to negative 3, and then divide by 7. So x has to be greater than or equal to negative 3/7. For the next, we're going to add 6 to both sides. So that would leave us 5x is greater than or equal to 6. And then we divide by 5. So x is greater than or equal to 6/5. So now you say, well, what's our domain? Do we put both of these on the number line? And the answer is no. We choose the one that's the most restrictive. The most restrictive would have the least number of values associated with it. So if we look at the number line for both of these separately, the first one begins at negative 3/7 and includes negative 3/7 and everything to the right. The second one, x is greater than or equal to 6/5, begins and includes 6/5 and everything to the right. So notice this area in between negative 3/7, excuse me, and 6/5 isn't included in the second one. So it is more restrictive. So our domain for this particular problem would be x is greater than or equal to 6/5, and in interval notation, 6/5 to infinity, and again, 6/5 would be included since it's greater than or equal to. So here we have a problem. Find the domain of f plus g of x when f of x equals 2x minus 7 and g of x equals 3 over x minus 10. Since we're adding, we can look at this particular problem and know that the only restriction occurs at our denominator. So we know that x minus 10 cannot equal 0. When we add 10 to both sides, x cannot equal 10. So come to your number line, put in your boundary point. Can't equal means that's the only thing that's not included on the number line. So everything to the left is included and everything to the right. So anything from negative infinity to 10, not including 10, remember, union with, because we have two intervals, from 10 to positive infinity.